Hey guys, Mr. Milton here. Today we're going to talk about angle measures and segment lengths. At the end of this video, you should be able to find the angle measures within a circle, and you should be able to find segment lengths within a circle. Okay, so we're going to go through a couple theorems concerning the measure of an angle inside a circle. So, the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So, if you'll notice here, we have angle 1. Okay, we have the intercepted arcs x and y, and so we could find the measure of angle 1, because we know the measure of angle 1 would be 1/2 the measure of arc x plus the measure of arc y. Okay, so it's just half the sum of those two angles. Okay, so that is how we find the angles between two lines that intersect inside of our circle. When lines intersect outside of the circle, the measure is half the difference of the measures of the intercepted arcs. Okay. And so you'll notice here there's a few more instances, or at least a few more things, ways that it will look. So whether we're talking about angle 1 here, angle 1 here, angle 1 here, notice that this angle is created outside the circle by lines that go through the circle. Okay, in this case we have a chord, or two chords, a chord and a tangent line, or two tangent lines. But the way that we find it doesn't change. It will be 1/2 the difference. And I know that you want to make sure that you find this the correct way, so you want to find the larger arc and take the smaller arc from it, but realize that there is no such thing as a negative angle. So if you're using the correct arcs, if you get, let's say, negative 32 degrees, realize that you put them in the wrong order, and it should be a positive measure. Okay, so we have a few examples down here. I'll scooch this up just a touch. Okay, let's see if that worked out. Alright, so a few examples here where we're finding the measure of the angle. First problem here, we're trying to find angle x. Angle x happens inside of our circle, and so we know that this should be x should equal 1/2 of the intercepted arcs. In this case, it'll be 46 and 90. Okay, because it's inside the circle, you know we're adding these two numbers together. 46 plus 90 gives us 136. Half of 136 gives us 68. So x is 68 degrees. Where x is 68, that angle is 68 degrees. Okay. Number 2. Notice here that z is one of the arcs. Okay, so we're not necessarily trying to find the angle. We already know that the angle created by the tangent and chord is 20 degrees. So 20 should be 1/2, and since 20 is outside, 95 z, since 20 is outside, we know it's the difference of these two. Okay, so now I'm solving for z. I'll multiply both sides by 2 to get rid of this 1/2. And so 40 equals 95 minus z. Subtract 95 from both sides. Gives me negative 55. Yes, negative 55. And that means negative z is negative 55, and z must be 55. Okay. Alright. For number 3, find the measures of each indicated arc and angle. Here, for number 3, I don't have, oh, it's just arc TH. There we go. That's what they want us to find. Arc TH. Measure of arc TH. So this is a little bit of a challenging problem in the sense that it feels like they didn't really give us a whole lot of information at all. We see that this angle 50 is happening outside of the circle, so we kind of can set up 50 equals 1/2 of something minus something, right? Because it's outside the circle, and that's just us referencing our formulas and kind of thinking about that. But there has to be more to this problem. I mean, we have to have more information to this problem in order to solve for the arc of TH. So here's how you can do this problem. Notice that they told us that the arc WH is 100 degrees. Okay, so we know that between TW and TH there should be 260 degrees. We don't know how that's split up, but we know between the two it should be 260 degrees. So what we'll do, what I'll do, I'm going to call TH x. Okay, so TH is x, that's what we're trying to find. I'm going to call TW, because I know this whole thing, WTH has to be 260, I'm going to call TW the rest of 260 after we take away x, or mathematically, 260 minus x. Okay, and so I'm going to take the bigger number first, minus the smaller number. 260 minus x. Alright, looks like a phone number here. Alright. So, what I'm going to do inside here to simplify, so we can make sure we understand why things are happening now as they are. We have x minus 260, we'll distribute that to the 260, plus x. And so in here I actually have x plus x, which gives me 2x minus 260. Equals 100. Okay, I'm multiplying both sides by 2. Okay. Alright, so adding 260 to both sides, I find that 2x is 360. Divide by 2, I find that x has to be 180. And since I defined x as the arc TH, then there's our answer. So we found out that this must be 180, and then this must be 260 minus 180, which is 80. Okay, so here's our real answer. Okay, a little bit of a challenging question, but that's how we go through it, finding out with just a little bit of logic and our equation for angles that meet outside of a circle. On to the next side, where we talk about segment lengths. Theorem that shows itself in a few different ways, and it goes like this. For a given point and circle, the product of the lengths of the two segments from the point to the circle is constant. Okay, so there are 3 times that it happens. It happens when the point's inside the circle. It happens when the point's outside the circle and one of the lines is tangent. And it happens when it's outside the circle and no lines are tangent. Okay, we've already actually talked about in 10.3 when the point happens outside the circle and both lines are tangent. So you can reference that back, but they're congruent, so not a whole lot to talk about. Okay, so here's what this theorem says. If we're talking about point P, so here we're talking about point P. For the pink line, the lengths of the segment from the point to the circle are represented by A and B. Basically, from P to this edge of the circle is A, from P to this edge of the circle is B. Okay? And for the blue line, C and D. Again, from P to this edge of the circle through C, this edge of the circle through D. This theorem says the product of the lengths to the circle have to be constant. So that means A times B would equal C times D. if it's outside the circle and one of the lines is tangent, notice they're meeting at point P. So from P to the circle, this edge of the circle is y. And from P to the other edge of the circle is y plus z. Okay, for the blue line, notice that this is a tangent line. It only touches the circle in one place. So basically, we have t from here to here and t. They're the same. Okay, because it only touches in one place. Therefore, our equation when it's outside the circle with one line that's tangent is going to be the product of y times y plus z and t times t, or t squared. Okay. And then finally, the final situation that our theorem covers is that if it's outside and none of the lines are tangent. So for the pink line, we have y and y plus z. And for the blue line, we have w and w plus x. Those are the lengths from the edges of the circle. Okay, and therefore we have y times y plus z equals w times w plus x. Okay, now all that's with letters, and so I can understand that being a little bit abstract. We'll put it into practice down here. Okay, these three examples asking us to find the values of the variables. Okay, so here, for the first problem, we want to find the value for y. We'll use our theorem. This is a point outside the circle with no lines tangent. And so we have from the end of the circle 6, and then the entire thing from 6 to the other edge, 6 plus 8, 14. Okay, remember we're getting that because it's 6 plus 8. And that should equal 7 from this edge to edge circle, and then 7 plus y. So we have 6 times 14, which I'll do up here, which is 84, equals 49 plus 7y. Subtract 49 from both sides, that gives us 35. So 7y equals 35, divide by 7, y will equal 5. Okay, we should be able to double check to make sure that it works out, because 6 times 4 should be the same as 7 times 12. Or sorry, 6 times 14 should equal 7 times 12, which it does, they're both 84. Okay. Alright. Number 2, looking at this situation, our point inside the circle meets here, and we know that it has a product. The product of its distances from the edge of the circle should be constant. So here, we're given a line, 7 and 7. Okay, and here we're given 4.8. Oops. 7 times 7 should equal 4.8 times x. Okay, so 7 times 7 gives us 49. 4.8x. We'll divide both sides by 4.8. I'll need a calculator for that one. 49 divided by 4.8 gives us 10. Look at that. Not even on the screen. Gives us 10.2. So x is 10.2. Okay. Then finally we have the situation where we have one tangent line and one line that's not tangent. So from this point where they meet to the edge of the circle is 8. From this point where they meet to the other edge of the circle is 8 plus 16, or 24. Okay. Okay, and that should equal z squared. Okay, so that gives us 160, 192 equals z squared. Take the square root of both. Okay. 64 times So our answer Z would be 8 radical 3 if they asked us for it as a simplified radical. But if not, we just had to round to the nearest tenth. We could do square root of 192, which would give us 13.9. All right, so there we have it. Maybe I did too much there. I could have left some down here. Okay, there we have it. We looked at finding angle measures in a circle, and we also looked at finding segment lengths. Okay, looked at two theorems that showed itself in a few different ways. What to do with segment lengths when they met inside, outside, and outside the circle, and how to find angle measures when they meet inside and outside of the circle. All right, see you.